final talk of today. Let's hope the dog hasn't eaten his lecture notes. David Fisher from Indiana, subgroup, subexponential growth, measure rigidity, strong property T, and Zimmer's conjecture.
All right. So I will say that this is not the room I first gave a lecture in, like Uri, but it is the first room I ever gave a lecture in outside of the United States. So this has some nostalgic value for me from 2000. Unlike Uri, I can't remember who the organizers were of the workshop. Yes, and I also want to say about the title of this workshop, Approximation, Deformation, and Quasification. It's very interesting because many of our participants and speakers seem to have a very precise idea what these words mean, and the organizers meant them very poetically, and they're poetical enough that we were actually approached by a numerical analyst who wanted to come to our workshop because he thought they meant something relevant to him. Yes, there will be a little bit of that in my talk, and I'll explain it when I get to it. So throughout the talk, G is a simple Lie group. The rank of G will be at least 2. Gamma in G will be a lattice. For many of the things that are important, G will really just literally be SLNR for n greater than or equal to 3. Not because I need it necessarily, but because it makes some numerology that otherwise becomes complicated go away. And sadly, I won't be able to claim that gamma is mostly SLNZ just because the theorems won't apply to necessarily to SLNZ, but things are simpler for actually co-compact lattices. And what I want to start with is a vaguish description of Margulis' superrigidity theorem. I should spare myself writing. I'll always just say in this case, I'll just call gamma a higher rank lattice. So this says if gamma is a higher rank lattice, we have a classification of linear representations from gamma into, just to make clear it's a different number, GL, say, n of R. So you classify all linear representations of your group is the way I want to think of Margulis' superrigidity theorem right now. And the standard way to do this is that the corollary is the arithmeticity theorem. I'm going to give you a rather odd and easy corollary of this theorem. Corollary is that gamma is an SLNR, a lattice, and again, n is at least 3, and I look at any row from gamma into GL m minus 1 of R, then row of gamma is finite. So the classification of representations is such that there are none in dimensions lower than the one you would expect, or none that are infinite. Lattices are linear groups, so they're residually finite, so there are lots of finite quotients, but there really are no representations in lower dimensions. And the main theorem will be some sort of nonlinear analog of this corollary. One thing I should say about the corollary is I don't think you can prove the corollary without proving the full superrigidity theorem. For SLNZ, maybe you can, but for a general lattice, the corollary requires the full strength of the theorem. So by analogy to this, Zimmer in around 1983 proposed something called Zimmer's program. Where what we did was we took gamma, a higher rank lattice, M a compact manifold, and rho a homomorphism from gamma to diff M, and we asked, if we can classify these things. And now is the moment where you get to see how long you know me and how many times you've heard me make this joke. If you look at Zimmer's papers from the early 80s and what he actually says about this classification program, he's very good at hedging his bets. you can actually see the fact that he's now a university president in the way he carefully hedges his bets on what he thinks this classification should be. And to be honest, for the general setting of classifying all actions, it's still somewhat mysterious. There's now more cause for optimism that one can do some things, but the general picture is still, I'm not convinced I have a good conjecture in general. But there was one thing that Bob was willing to make as a clear conjecture, which is the following. And again, now I'm going to specify to S ln r, so gamma in S ln r n greater than or equal to 3 a lattice. M again a compact manifold. Rho from gamma to diff m. Then we have two things that are expected. One is if the dimension of m is less than n minus 1, then rho of gamma should be finite. And two, if the dimension of m is less than or equal to m minus 1, omega is a volume form, and rho gamma preserves omega. Then, again, rho of gamma is finite. So this is the conjecture, and as I said, I'm stating this for S ln r just because then these numbers get to be m minus 1. If I state it for a general lattice, I have to tell you what these numbers really are and how you compute them, and this would waste 5 minutes and not enlighten anyone. So I'm not going to do that. I'm going to explain where those numbers come from by giving you two examples. First example is that S ln r acts on, well, either Sn minus 1 or maybe more naturally on Rpm minus 1. So gamma does too. This shows that the dimension bound in the first half of the conjecture is sharp, because this, the representation of gamma in here is faithful and not finite. Second example is that S ln z acts on the n torus, which is, Rn mod Zn. And so the second half of the conjecture is also sharp. I need that to be n minus 1 in order to avoid this example where my action is obviously not factoring through a finite group. So, the conjecture is you can't make lower dimensional examples than this. And to cut to the chase, the theorem, which is joint with Aaron Brown and Sebastian Hurtado, is that Zimmer's conjecture is true for gamma co-compact. So this is really what I'm going to tell you about today. The sort of parenthetical is, it's also true for S ln z. But this is something we haven't, this is actually on the archive, you can read it. So there are some caveats here that I'm happy to explain more about at the end, but we get a result for every simple group. For SLN and SPN, it's sharp. For other groups, it's not quite sharp for reasons that, basically, it stops being sharp when the root spaces are high dimensional. We get a very good result, but there's something that goes wrong when they're high dimensional root spaces that I think will be fixed soonish, but right now it's sharp for S ln r, and it's not quite sharp if you want to look at SOPQ. Every split case it's okay. And it probably, probably within a year I'll be able to tell you it's okay in the other cases as well, but right now we can't.
At the beginning you made a comment and you said the Zimmer had to make a conjecture very carefully.
Yes. This one he made very clearly. It's in print in several places in around 1983. There was no hedging on this one. This one he really believed.
Okay. So which one?
we can talk about it later. I don't want to go into other conjectures that I'm not talking about today.
So this one is very precise and not
Yeah, no, this is very precise. And I want to give, I'm going to give you a cartoon of history. It's a very self-serving and silly cartoon, which is that the history up until now is roughly the fact that there was a theorem that says, I'll explain the attribution later, that if gamma is an SL3R and is not co-compact, the conjecture is true. So this really was the only full case of the conjecture known up until now. Really more was known. So if you look at SL3R, the nice thing about SL3R is that, well, n is 3, so n minus 1 is 2, and less than n minus 1 means dimension 1, so you're only worried about dimensions 1 and 2. So for this one, you have two cases. One is S1 and the other is a surface. In this case, Whitty-Morris proved the conjecture for gamma mapping even into homeo of S1 for some lattices. And then that's what is in about 94. And then independently, Berger, Monod, and Gis proved the conjecture for all gamma mapping into diff S1. And here I should make the point that this one includes gamma co-compact. And that's in about 99. My dating conventions are a little weird because some of them are going to be the years of the papers, and the ones that happened after I was on the scene are going to be more the year of the proof. So they're a little odd. So that really takes care of the one-dimensional case. And for surfaces, there's then a theorem that is proved independently by Polterovich and Franks and Handel in around 2002, I guess, that says that for any gamma non-uniform, any row from gamma to diff S omega has rho gamma finite, where here S is a surface and omega is a volume form. So that really is, so they prove more than you need just for SL3R, but the results they get are only sharp for lattices in SL3R. And now you should be wondering, I said Zimmer was very clever and hedged his bets in the program, and that he made a very precise and sharp conjecture in this case, and clever guy who hedges his bets makes this very broad conjecture based on, 20 years later, there's almost no evidence for it. So I want to tell you why Zimmer actually believed the conjecture, which is just going to state for you something that I'll call Zimmer's co-cycle superrigidity theorem, even though it's only a special case. And I'm going to state it in a way that's slightly different than it's usually stated in the literature in this context, because I'm going to state it in the way that I'm going to use it somewhat later in the talk. So again, I'm going to take, and again, gamma is going to be an SLNR, a lattice, n is going to be at least 3, m is going to be a compact manifold, the dimension of m is going to be less than or equal to m minus 1, and I'm going to have rho from gamma into diff m, and the statement is that then for any gamma invariant measure, mu rho of gamma preserves a measurable Riemannian metric which we'll give a name G. And here I'm usually better at this. Mu measurable, if one wants to be precise. So in this case, there's an invariant metric as long as there's an invariant measure. So now I should confess that Zimmer did make this very precise conjecture, but only the second half of it. The first half of it was added by Farb and Shalen about 16 years later. By the 16 years later, when Farb and Shalen made it formally in a paper, Zimmer clearly had believed it for at least 10 of those years. So, who gets credit for the more general, for that case of the conjecture is a little fuzzy for me. But it's only stated in the literature by Farb and Shalen. And so what Zimmer's evidence for this was he had this measure. If you make this volume, smooth volume, or really this measure, smooth measure, or even any measure of full support, you have this measurable metric on the whole manifold. And you think, oh, if my measurable metric were, nicer, it would be good. And so the remarks are that, one, if G is smooth, or even continuous, or even just bounded, then the conjecture follows. And this is just, when I say these various things, this is trivially obvious because the isometry group of a smooth metric is known to be a compact Lie group. I'm now looking at a homomorphism from gamma into a compact Lie group, and Margulis will take care of it for you because compact Lie groups are linear. You have to argue a little harder in these other cases, but Zimmer knew how to do that. The other remark to make is that, to just point out how odd this is even if the support of mu is equal to m, G doesn't define a distance on m. When I say I have a measurable Riemannian metric, I really have at each point, I have the GIJs of a symmetric inner product at the point. They vary measurably in the point. They can blow up. They could blow up at a point. They could blow up on lots of sets. They could blow up on lots of Cantor sets. You could obstruct almost any interesting path in your group from having finite integral. So you can't use this thing to define a path metric when it's at this level of regularity. So it's a very bad object. And Zimmer bravely believed that it should turn out to be more regular and therefore useful. The fact is that if you want to get a distance function, exactly what you need is boundedness of the Riemannian metric, and that's why that case is that's the minimum you need to finish is a bounded metric because it gives you a distance function, and once you have a distance function, you can finish. So the other thing I should say is Zimmer didn't just have this theorem. He had about 30 odd theorems at the time where he could prove under some hypothesis or other that G was then a smooth metric. And so, he really had what he felt was a bunch of evidence. He was not making a foolish bet. I want to address the question, what does it mean to preserve this funny G that I just said, it's not even a distance function on my manifold. It's not a very good geometric object in any sense of geometry that we're used to. And before I do that, I want to just give you an a priori estimate that's true for any row from any gamma to the diffeomorphism group of a manifold, provided, of course, that gamma is, as all of our groups are today, finitely generated. And this is just that if I look at the derivative of a row at a group element gamma at a point x, I take the norm of this. And now here there's a point that I can never tell if I should make in talks or not. I'm actually measuring this norm with respect to some inner product. I'm going to measure it with respect to G0, and what we're just going to do is going to fix G0 a smooth metric. It's not invariant, we're not worrying about that, but we're just fixing it so we can measure things. Well then this is less than or equal to some constant times the length of gamma. And what is this? This is just the chain rule. Right? I have my generators, I write gamma as a word in my generators. each generator is a diffeomorphism of a compact manifold, so it's only so big. I compose a bunch of these things, I get whatever that size is to the size of the number of generators. So, this is just the chain rule. I have this kind of a priori growth. If gamma preserves, G0, then we get a much better estimate, which is that d rho of gamma at x is always equal to 1 with respect to G0. But we don't have this. We only have that it preserves this funny G. And so the question is, what do I get? Do I get anything better than this from preserving this funny G? And the fact is that I do. Preserving G implies the following, which is that if I look at the limit as the length of gamma goes to infinity of the log of the derivative of gamma with respect to x, G0, and I divide by the length of gamma, yes, I've got all that right, I get 0. And this has a name. This is called 0 first Lyapunov exponent. But I should be clear that this holds only for mu almost every x. We have this property, we have this invariant metric. It doesn't tell us a lot because it's a terrible, terrible object, but it does tell us that in some weak asymptotic sense, my derivatives, when I compose them, when I look at large words, the derivatives aren't growing at a fixed exponential rate as expected a priori. They're growing at some kind of subexponential rate. But the problem with this estimate is they're growing at a subexponential rate in a bad way, because this is mu almost everywhere. The rate of convergence actually does depend on x, and the rate of convergence also depends on which sequence of elements I pick going to infinity. So this is some sort of subexponential growth of derivatives in some very weak sense. And what I want is subexponential growth of derivatives in a stronger sense. So I'm going to give you a definition that's sort of the pivot point of our proof, is the following definition, which is one of these things where you start working with it and feels like this should be in the literature all over the place. I believe it first appears in a paper by my collaborator Hurtado. So definition that, while written before our paper, actually hit the archive after our paper. So I have rho from gamma to diff m has subexponential growth of derivatives if, we can get some quantifiers. For every epsilon greater than 0, there exists some c greater than 0, such that, and let's just make this clear, we'll take the sup over x and m of d rho gamma at x, and this will be less than or equal to c e times epsilon to the length of gamma. So this says that, rather than growing again at the a priori rate, which is a fast exponential, this thing grows slower than every exponential function. And the easy exercise in whether you understand the definitions is that subexponential growth of derivatives implies 0 first Lyapunov exponent. But that's sadly going the wrong way, because we know we have this 0 first Lyapunov exponent. Why is this better? This is better just because, this suping over x and m is important here, because it says I have this estimate at every point and I have it uniformly at every point. And so this is, what one really wants. And now maybe I'll go back over here. I want to tell you a little bit about a very classical and easy proposition that somehow is the thing that motivates our strategy of proof, which is there's a stronger relationship between these two things, at least if you look at actions of z. So this is a proposition that I actually think it's relatively hard to find this in the literature, but it's implicit in many more difficult things that are in the literature. So if I have rho just from gamma to diff m, then rho has sub-exponential growth of derivatives if and only if rho has 0 first Lyapunov exponent, and you should be hesitating a second as wait, these things are just equivalent. There's an important caveat here, which is for all z invariant measures. Oh, thank you. Gamma is equal to z. Proposition is really only true for z. You can make a variant of it for z to the k. You can't even make a variant of it for all amenable groups. There are problems with that. But what I'll tell you about the proof of it is just about amenability. I mean, this is actually an easy compactness result of some kind. It's also an approximation argument, so it's where I get to, justify my connection to the title of the conference. And what's the argument? Is, well, if this action doesn't have sub-exponential growth of derivatives, what does that mean? That means there's some x's where when I apply longer, for each length of word, there's some x at which I have derivative that's at least epsilon, e to the epsilon L of gamma for some fixed epsilon. So what we do is we pick points xi where, in this case, there's only one word of length, really only one word of length I, where rho n xi has derivative bigger than e to the epsilon naught n. This is just what you get by converting the converse on the definition. And then you just look at mu I to be the obvious measures. You take sum over 1 from m plus 1, I equals, j equals 0 to n of the Dirac measure at, let me just give this a name. Rho of 1, we'll call it f, because writing rho of f here I find confusing myself. So I just take the obvious measure on the orbit segment. And the fact is that mu i's converge to some mu. Here I'm using, I didn't really say this carefully, I didn't tell you that m was compact. But m is compact, and so these mu i's converge to some mu, which we all know in this room is an invariant measure. This is invariant, and for this measure, it will turn out that, this limit of d rho to the n x log of that over n will be at least epsilon naught. And you have to check that this is true, that this limit will be this. There are only two ingredients in the rest of this proof that I'm not going to tell you. The two ingredients are Kingman's theorem, the subadditive ergodic theorem, and the chain rule. It's the only thing you need to know to prove the rest of the proposition. It's really, it's a very easy proposition. And now, somehow the point, though, is that this is bad for us because why could I get away with this compactness result? I can get away with this compactness result because this construction that we all know, that's the construction that motivates the definition of amenable group, works for amenable groups. So in particular, it works for Z. And we have lots of invariant measures, and we have enough invariant measures to somehow detect all the exponential growth you might see. And there's a problem, in that my group gamma, we all know, isn't amenable. And so I can't apply this directly. And that's, the first big mystery. And I'll tell you how we resolve that in a second. I want to first, tell you where we're going for the next half hour. So I'm going to give you the recipe of the proof, how you cook the theorem. Sometimes I call it an outline, but what I'm giving you is really much closer to a recipe. So first, what do you want to do? First, you prove subexponential growth of derivatives using several ingredients. First is, some hyperbolic dynamics and just the theory of Lyapunov exponents. Second is homogeneous dynamics. And some results of Ratner on unipotent flows and some consequences of those that are theorems of Shaw, Shaw. And then you also use a very recent theorem of Brown, Rodriguez, Hertz, and Wang. That this theorem falls in the category of things that are usually nowadays called nonlinear measure rigidity. And hopefully I'll get to tell you at least a little bit about their theorem later. So we need all of these things. So this is step 1. Step 2 is find an invariant smooth metric using Laforgue's Strom property T. Well, we use that, and in this case we're using work of Laforgue and of de la Salle and de Latte. Half the reason I'm giving you the recipe is to give credit to all the people whose work has been very handy to us in the course of doing this. And the other thing we use is some things from dynamics. We use some Sobolev space theory. And some things called estimates on compositions that in this context were worked out in my work with Margulis. So that's by way of thanking all the people who actually made this work possible. And also giving you sort of an outline of where we're going from here. So and I will say that, from some point of view, there's some, fairly heavy machinery in this proof. There are a bunch of large theorems we're using. I lied a little bit in the first part of the outline. I'm also going to use Zimmer's cocycle superrigidity theorem that I stated earlier in that part of the proof as well. And I will say that, the second half of the argument is much shorter and easier than the first half. And you can even go so far as to say that the black boxes in the second half of the argument are a little lighter than those in the first half. Because when I say we're using Ratner's theorem, there are a bunch of cases of Ratner's theorem that are relatively easy to prove at this point in history. We're not using those. We really need the full force of Ratner's theorems for unipotent subgroups and equidistribution. We can't get away with anything less than that currently. That's sort of the heaviest of the black boxes in here, in my own opinion. So what do we want to do? First thing we want to do is fix this problem we had that we can't use the proposition because G is not amenable. We do need unipotents. So we also, Emmanuel's asking me, wait, you're saying you're using Ratner's theorem, you're using unipotent flows, where are the unipotents in gamma? If gamma is co-compact, there are no unipotents. And that comes in exactly the same way where I fix the problem that gamma is also not amenable. And the fix is this following standard thing, which is, from the gamma action on M, I can build a G action on some space, which we write this way. Right, I take, G times M and quotient out, by the right action, where g times m times gamma is g gamma inverse rho gamma m. That's an action here, and the point is that g can still act on the left on itself. So this is a g space. From my gamma action, I build a g action. At least now I have an action in which there are some unipotents. And now what do I do? Because, from the other point of view, I've at least found some unipotents, but gamma was non-amenable. G is still also equally non-amenable. I haven't helped myself too much. So we use just the Cartan decomposition. G is K, right? Where in this context, this is just SON, and this is just the diagonal matrices, right? So this is not a mysterious decomposition in this setting. I just decompose this way. And then what I do is I pick a K invariant metric on this space. So what does that tell me? It tells me that if my derivatives are going to grow, these things act as isometries. So again, by a trivial application of the chain rule, what do I know? I know that if, I'll come back to this in a second. If G has exponential growth of derivatives, by which I just mean that it doesn't have sub-exponential growth, so does A. And this is the reduction from this non-amenable group to this amenable group. And now I have to fix something where I haven't quite told you the truth yet, right? Because I'm looking at this G action on this G space, which is G cross M over gamma. There are two sets of, if I look at the tangent bundle to this thing, that splits as directions that are tangent to G times directions that are tangent to M. On the directions that are tangent to G, I know what my derivative is. It just comes from the adjoint representation. Those derivatives grow exponentially. But they also don't matter for my problem. So, from now on, and when I write d rho of G at a point x, what I really mean is d rho of G restricted to the tangent space to M at, this point. Really, I should be writing it as G comma x at the point G comma x. So I really only care about my derivative along the fiber direction. So this is, the fiber derivative. And there's one more fact I need. It's actually completely trivial, but I'll state it as a fact because it's also odd, and that it's one of the things that goes wrong in the proof if you try and make gamma not a uniform lattice, which is that sub-exponential growth for gamma is equivalent to sub-exponential growth of fiber derivatives for G. In this, this is sub-exponential growth on here. This is sub-exponential growth in the fiber direction here. Those are completely trivially equivalent, except for the fact that the trivial equivalence uses gamma co-compact. And now, so I've done this, and I now have this group A that is amenable, to which I want to sort of apply the logic of the proposition. And all I'm going to tell you is that I can. And so, what does that mean? That means, how did I decide to state this? The upshot of the conversation so far is just that, if gamma doesn't have sub-exponential growth of derivatives, And, well then, there exists some mu, an A invariant measure on G cross M mod gamma, and I'll just say it this way, and an element A in A with, you know, this same property that if I look at the limit as n goes to infinity of log of d rho a to the n at x over n, that's equal to some lambda that's greater than 0 for almost every x. And this really follows, this conclusion follows from exactly the same argument as this classical proposition does, with almost no changes. And I should tell you, I'm lying to you about a few things here, especially when I write this as equality, right? Really, I want mu also to be a-ergodic. So really over there, all I had to care about was ergodic measures too. I'm just avoiding ergodic decompositions to avoid technicalities. They don't introduce any serious difficulties in the arguments. But in case the experts are wondering, you know, and the fact that this limit exists is this is the first Lyapunov exponent, which we know is defined. The proof that it's defined again is the chain rule plus Kingman's subadditive ergodic theorem. Once the measure is ergodic. So what do we do with this now? So I'm going to give you the outline of the rest of this argument. There's a goal now. What you're supposed to remember right now is that I told you that by Zimmer's co-cycle superrigidity theorem, I couldn't have this number be positive, except that was for G invariant measures, and this is just an A invariant measure. So the strategy is the following. Promote mu to a G invariant measure u prime, which then contradicts, you know, when we have to do this, preserving this condition that lambda is greater than 0, and contradicts co-cycle superrigidity. So if I can do that, then what have I done? I've contradicted co-cycle superrigidity, and so the statement that gamma doesn't have subexponential growth of derivatives has to be wrong, and gamma has subexponential growth of derivatives. Now I have to decide how much I want to say about this. You know, how do we achieve the goal? To achieve the goal, there are also two steps. I promise I won't divide the proof into too many more pieces and create a fractal for you. Step one is use averaging over unipotence. Well, let me before I say this, there's this map pi that I haven't bothered to tell you about before, but many of you know it's already here. There's a projection from this space G cross M mod gamma down to G mod gamma. Just forget the second coordinate. And so what we're going to do is use Ratner and Shaw's theorems to average mu over unipotent subgroups so that the result has pi star mu prime equaling har. Right, we're projecting this measure down to G mod gamma, the measure we started with is projection to G mod gamma is just some A invariant measure. You might still hope that's good if you know enough measure rigidity theorem and you're familiar with the theorems of people like Lind and Strauss. There's no way in this setting to prove that that measure has positive entropy, so to use any of Lind and Strauss's results, it's some sort of non-constructive thing that, you know, could have positive measure, we just use his theorem. Although the measure classification there is still a little complicated, so we'd have to use his theorem plus something. Turns out that the best way to deal with this instead is just to start averaging your measure. And you can do this, the fact that you can do this preserving the positivity of the first Lyapunov exponent and preserving the A invariance of your measure is not a trivial thing. This is probably the hardest thing in our actual paper. And the second part of this is to, you know, use this then Brown, Rodriguez, Hertz, and Wang very luckily come along and tell you that implies mu prime is G invariant. And this is something of a, you know, this isn't a miracle because we started from this point. You know, we knew their theorem. We were working with one of the authors. We were headed for this point. This was this, you know, kind of looks like, oh, these guys just proved the rest of your argument for you, and it's not true. That was where we started from, was knowing they would do this. Right, and maybe I should be clearer here. You know, here, mu prime is A invariant, and lambda is still positive. That's what you know at the end of this step. It's A invariant, it projects to Haar. If you read their paper, if you read the introduction to their paper, they seem to need, you know, their theorem is about mu prime P invariant rather than just A invariant. Mu prime is P invariant, its projection to the quotient is automatically Haar by a result that predates Ratner's, but I think is also, I don't get that wrong, it's either due to Ratner or Furstenberg, or maybe Dunny. But if you look at their actual proof, there's a proposition in their proof that we can use to, you know, sort of soup up their arguments by doing some extra algebra to actually get this G invariance. There is something in that argument that really isn't theirs. There's some extra algebra we have to do to get this to be G invariant that's not in their paper. But it's not very hard. And I will say, these steps are more involved. If I had another hour, I could basically give you the outline of how this goes. Or maybe an hour is a slight underestimate. If I had an extra hour and you're willing to swallow a lot of Ratner theory very quickly, I could tell you how this goes. You know, we don't have to, you know, yeah. The other thing I should mention is that here, there's a key ingredient here that one should mention too, which is some work of Ladrapier and Young. I will say that if you're at all curious about measure rigidity results and you've never bothered to go read any, because they look daunting and challenging, which they often are, this Brown, Rodriguez, Hertz, Wang paper is in some sense one of the softest and easiest. You know, Ratner doesn't use Ladrapier Young, but Margulis and Tomanov rewrite her proof, so it does. Lind and Strauss uses Ladrapier Young, Katak and Spotster use Ladrapier Young. This is the machine that makes measure rigidity arguments work at the bottom of it. And this is probably the simplest application of it that I've seen. So there really is something to be said for this paper in terms of, you know, educational value too, that you can learn something about how measure rigidity theorems work without having to sweat quite as much as you used to if you just read their paper. You know, the paper's about 25 pages long. To get to the point that we've used, you only need to read about the first 9 pages. All right. So now I want to tell you about, you know, if I had another hour, I could tell you more about these things. I don't, so instead I'll tell you a little bit about strong property T and how the argument finishes. I can't tell, you know, This is definitely not a homogeneous or smooth dynamics audience, and so maybe this is of greater interest anyway. This is this great notion of Laforgue's. And I'm going to define it slightly more slowly than he usually does. I break the definition into two parts. Say that I have some representation of some group gamma into bounded operators on some h. H is just going to be a Hilbert space. This is bounded operators on h. We say this has epsilon sub-exponential norm growth if, well, what? If there's some constant c greater than 0 such that the norm of rho of gamma is less than or equal to c e to the epsilon length of gamma. That should look very similar to what we saw before. And this really is a happy accident that he had handled this before we needed it. Then there's a definition where I'm going to lie about a couple things, just because this definition is a little bit too complicated. Maybe before I lie about them, I'm just going to fix something that I think is fairly standard for this audience, but I don't know. I'm going to let mu be some measure on my group. The measure is going to be 1 over the size of the generating set, sum of Dirac measure at x, and if I apply, I don't really want to call that rho, I want to call that pi. If I apply pi of mu to a vector, what I mean is take 1 over the size of s, sum over s in s of pi s of v. So this is just some operator. It's the averaging operator for the equidistributed measure on generators. And then definition, gamma has strong property T if there exists some epsilon naught greater than 0 such that for all epsilon less than epsilon naught and all pi from gamma to b of h of exponential of epsilon sub-exponential norm growth pi of the convolution powers of mu to the nth power converges exponentially fast to projection on invariant vectors. That definition looks a little cumbersome, and I'm going to tell you what the last part of it means, and I'm going to explain why you shouldn't be as scared of it as you might be. What I mean here is that if I look at, there's some projection, p from h to the h invariant vectors, that's my projection, and pi of u star n minus p in norm, there's some lambda less than 1 is less than, and some constant greater than 0 less than c lambda to the n. So this is approaching this projection very fast. And why shouldn't you find this as it's a complicated thing with many quantifiers in it. But what's the point? The point is, property T is supposed to be about finding invariant vectors. Any representation with almost invariant vectors has invariant vectors, is our usual definition of property T. In this context, then that definition gets bad, because if my vectors aren't almost invariant, that's just not a good notion, because my vector might not be almost invariant just by being stretched a little or contracted a little. And the standard arguments for how property T is supposed to work go awry. It is true that if this, instead of being a representation by bounded operators, is a unitary representation, then this is exactly the statement of what comes out of property T. It's, that property T means that averaging your vector converges fast to your invariant vector. This is something that you can deduce from the standard definitions by a little bit of convex geometry, really. And in this context, you need to work with this definition of property T and generalize this definition of property T rather than the ones that are a little softer and less quantitative. And that's just a fact of life as far as I can tell. And maybe part of the reason why strong property T has not become a boom industry quite yet. It's a little harder, and not all the equivalent definitions are equivalent. The other thing I should say is I lied in here quite blatantly, which is that mu, I can't really take that mu. I told you I was taking that mu to make people more comfortable who have seen property T before. There's some other measure I can take. In Laforgue's papers, and in the first few papers of Delassalle and Delassalle-Delatte, they take mu sub n, which is, instead of being convolution powers of one measure, you take a sequence of measures that's given to you in some sense by God. And Mikhail, in a recent paper, proved that you can just do this instead. You pick some nice enough measure and then take its convolution powers, which to me feels more natural. But even those things are complicated and only being understood recently. So this is what strong property T says. And how are we going to use it? What we're going to do is, we have gamma has sub-exponential growth of derivatives. I'm going to look at some space, which I'll write as W2K of M S2 of Tm omega. So this is some Sobolev space of symmetric forms on M. And my action row of gamma on G defines a representation of gamma into here by bounded operators. And now we have to worry about a few things, one of which is, you'll notice I have K here. I'm taking more than one derivative. If you know anything about Sobolev embedding theorems, you know I want to take more than one derivative. And in fact, I want more than one derivative for an even sillier reason. If I want to take any derivative of a symmetric 2 tensor, I better have 2 derivatives of my original map. That's just a fact. That's how you act on tensors. And now I want to, so I want to say that this is going to have epsilon sub-exponential norm growth, but I'm taking somehow lots of derivatives instead of just one. And so far I've only been talking about one derivative, but this is where using estimates on compositions, which is really a fancy consequence of the chain rule, sub-exponential growth of derivatives implies epsilon sub-exponential growth and epsilon sub-exponential norm growth for all epsilon greater than 0 here. So there's one other thing that I'm lying to you about a little bit is, I threw in a volume form here to be able to define a Sobolev space. The volume form is also not necessarily invariant. But the Jacobian that takes care of the change of the volume also just depends on the size of the Jacobian, just depends on the size of the derivative. And so that also just folds into your sub-exponential growth. Everything just folds in together. And you still have this. And now what do? You just pick your favorite smooth metric, G0, and you look at whatever I'm calling this, rho u star n G0, and this converges to some G, say, final, which is gamma invariant. By the Sobolev embedding theorems, if I had enough derivative, if I made this K big enough, which I'm allowed to do because this machine works very robustly, this thing has some derivatives. it's at least C1. If you're very careful with your arguments, you can arrange for this thing to be C infinity if your action is. It's not very hard. But the thing you have to worry about now, and the reason why I had to tell you more about the definition here than I might have, which is the reason why I had to tell you this thing, is that why is G fin non-degenerate? It turns out it can't be of funny signature. It can't have negative directions just because it's a limit of positive metrics. So a limit of positive things can have 0 directions but not negative directions. But why is it non-degenerate? And the fact is that because we're getting to our invariant metric so quickly, and because our derivatives are only growing slowly, it works out. This is an easy computation using star and sub-exponential growth of derivatives. The point is really that if I look at a vector and I start averaging it, start averaging my metric and applying it to my vector, the size of that vector can only shrink sub-exponentially quickly, and it's becoming, the thing's becoming invariant exponentially quickly, and so in the net, you reach an invariant metric before the vector shrinks to 0. It's really an easy argument. And with that, the proof is finished. So thank you.
You have any questions?
Yeah. I do have a question on the strong property T. So the projection that you take is the orthogonal projection on fixed vectors, right?
Yeah, when I'm working in a Hilbert space, yes.
But could it be some oblique projection, or I mean?
So
There is no reason why it's orthogonal. You just take a unitary and you conjugate by a non-unitary, then this projection will be the same, but it will no longer be orthogonal.
Yes.
Yeah, well, it really doesn't need to be in general. In this context, it can be.
Yeah, but the question is, well, is about that definition. So do you need the orthogonal projection? Or
No,
not?
I don't need the orthogonal projection. I need a projection.
Some projection.
Some projection on invariant vectors. I don't need the orthogonal projection. You get a projection on invariant vectors that's handed to you by the machine. That it doesn't have to be orthogonal projection.
Okay.
In the Hilbert space context, no, you're not even there. Can I arrange it to be orthogonal projection? Okay, yeah. Okay.
But it's parallel to the unique complement space subspace which is invariant by the action.
Right.
It is what the equivalent of the...
Right, so if the action is unitary, then I can take it to be orthogonal projection. But if the action isn't unitary, I can no longer do so. That's right. Anything else? Growth of derivatives. So first you use this easy compactness argument to find an A invariant measure with positive first Lyapunov exponent. And then you want to make that A invariant measure G invariant. And there's several tricks here, right? And I'm really using the fact that I have invariance under this big abelian subgroup. So what I basically do is I say, oh, I'm going to give up some of my invariants. I'm going to look in some singular direction, where I then commute with some unipotent. I'm going to average over that unipotent, and then I have a new measure that's invariant under a smaller piece of A and some of U, and that makes my projection nicer. And then I can average over A again, and you can argue, and this is really where you need Nimish's results, you can argue that averaging over A again doesn't change your projection. So your projection remains invariant under all of A and under some unipotents. And you do this until you've used up all your unipotents, essentially. You argue using the fact that this is where dimension comes in. You don't have that many fiber Lyapunov exponents, and you have, and you have few enough of them that you can get all the unipotents while avoiding them. And that comes in again in the use of Brown, Rodriguez, Hertz, and Wang, is where the low dimensionality really comes in. I've sort of hidden it. Why am I assuming my manifold's low dimensional? Why haven't I proved that the examples I showed you at the beginning don't exist? is because in making these averaging arguments and in using this Brown-Rodriguez-Hertz-and-Wang argument, you need to know that there are only so many Lyapunov exponents in the fiber. And that combined with knowing that there are lots of Lyapunov exponents in G lets you make these averaging arguments work.
Anything else? Well, if not, we'll thank David again for